to the wonderful world of transition elements. This is video number 3. Key aims for studying transition metal complexes set out here in the study pack. We need to be aware of colours of complexes and learn the specific colours for key complexes and compounds. Shape's important. That all depends on coordination number. Remember, coordination number is the number of dated covalent bonds made to that central metal ion. Thinking about shapes, we need to be thinking about bond angles. We've already looked at precipitation reactions. What we're going to be looking at next is something called ligand substitution. Substitution in both inorganic and organic chemistry means much as it does in everyday language. We're going to swap one thing for something else. We're going to swap one ligand for a different ligand. One molecule or negative ion for a different molecule or negative ion. So let's start with copper. Copper hexaaqua ion. Remember, we can write down the formulas of transition metal complexes by putting a metal, putting a ligand with the number of that ligand, in this case 6 waters, all in square brackets to signify the transition metal ion complex, and then any charge goes up in the top right hand corner. As we know, that's aqueous. So we've got our light blue copper hexaaqua ion. Now what we saw when we were talking about precipitation reactions, when we add a small amount of ammonia to our copper hexaaqua ion, you get that light blue solution becoming a light blue precipitate, because it's the hydroxide ions that are present in the ammonia solution that form that hydroxide precipitate. What we're looking at in this section in ligand substitution is what happens if we add lots of ammonia. What's actually happening to the complex overall? So we're starting with our copper hexaaqua. We are adding ammonia, NH3, and we can see by looking at the diagram on the right hand side, we form the dark blue solution of the copper ammonia complex. What happens is 4 water molecules that surround the copper are replaced with 4 ammonia molecules. So 4 ammonias, there's still 2 waters left over. The charge remains at +2, 2 plus, because there's nothing actually happened in terms of charged particles in the complex. We've got the central metal copper 2 plus ion, the ammonia and the water are all neutral ligands, so the overall charge remains the same. And we must have swapped 4 ammonias for 4 waters that come out and have been replaced with 4 ammonias. Looks quite complicated, but actually it's quite a straightforward swapping process. The difficulty is remembering the formula of what you make. It's 4 ammonias for copper. Now interestingly, we have got at the beginning 6 ligands surrounding the copper ion, and at the end we still have 6 ligands. So we have an octahedral complex at the beginning, and we have an octahedral complex at the end. Bond angle's 90 degrees, and we should be able to draw either of those or both of those 2 complex ions. We've got a ligand substitution and the shape has remained the same. Now when we do ligand substitution with chloride ions, something very, very different happens. We take our copper hexaaqua, this time we swap 4 chloride ions in, interestingly, all of the waters are replaced by those 4 chloride ions. So all 6 water molecules come out and 4 chloride ions go in. Now if we think obviously about the charge on the complex ion, we've got a copper 2+ ion at the centre. We've got 4 Cl- ions behaving as ligands, so overall the charge on this complex ion is 2-, and it forms a yellow solution. It's still a complex, so we can still, and probably it's better if we still put that in square brackets. I appreciate they haven't here on the colour sheets, the colour chart that OCR kindly provided to us. But it's not a problem to still keep that complex, that transition metal complex, inside a square bracket. Now there are only 4 ligands in the copper fluoride complex. And if we want to think about the shape of the copper chloride complex, we need to be thinking tetrahedral. You should know the shape, tetrahedral of the copper fluoride complex. Bond angle, as I'm sure you all know, think about that now, 109.5 degrees. That's something you should be able to draw. You need to know the colour, yellow. So we're going from the pale blue copper hexa-aqua ion to the yellow copper fluoride complex. This time, in this ligand substitution reaction, the shape has changed. We've gone from an octahedral complex to a tetrahedral complex. Also on the syllabus, we need to know about ligand substitution reactions of chromium to Cr3+ ion. Again, we're going to start with our chromium hexa-aqua ion. Pale purple. And the chromium hexa-aqua ion is going to react with 6 ammonias, and all of the waters will be substituted for ammonia molecules. Again, still 3+, and all 6 waters have been replaced. So it's a straightforward swap. As we've already mentioned, the good news about chromium is it's an octahedral complex at the beginning, it stays octahedral at the end. There are 6 ligands surrounding the chromium ion at the centre, and those 6 ligands, 6 waters, or 6 ammonias. Or when we're doing the hydroxide, in excess hydroxide, 6 hydroxides. So it's pretty straightforward in terms of learning the formulas. Just always think 6 of the same thing, whatever that thing is. Again, here are the colours for you to memorise. Pale purple, chromium hexa-aqua ion, going to a deep purple, chromium ammonia complex. If you want to name the chromium hexa-amine or amine complex. Spelling this time double M for amine to differentiate between the organic functional group of amine. So let's not worry too much about the name, but there is a difference. It's a chromium hexa-amine complex. Now, let's think about this idea to do with shape. We've just seen the copper 4 chloride ions. Well, that, when we're thinking about shapes of complexes, coordination number 4, that means there are 4 dated covalent bonds to the central metal ion, 4 chloride ions around the central metal ion, each one forming a single dated covalent bond to the central metal ion, gives us our tetrahedral arrangement. That would also be true if I were using cobalt, another very famous tetrahedral complex. You definitely need to know the colour of the copper chloride complex, yellow. The cobalt chloride complex is blue, a very dark blue. Now, interestingly, we have another arrangement possible for complexes with coordination number 4, and that is exemplified by platinum complexes, which are square planar. This time, I put my platinum at the centre of the complex. I could have this square planar arrangement. The coordination number is still 4. There are 4 dated covalent bonds to the central metal ion. And in this case, as an example, I could put 2 different ligands at the centre, surrounding the central platinum. 2 ammonias, 2 chlorides. Very, very important complex. Platinum is 2+. The chloride ions each have a minus charge. The ammonias are neutral. So overall, the complex has no charge. I could write this in 2 ways. I could draw it out. I could also just write the formula. So we've got different shapes of complexes. We've got examples of octahedral complexes, coordination number 6, and we have examples of complexes with coordination number 4, but there are 2 shapes, tetrahedral and square planar. And it's important that you know examples of all of these shapes, because an exam question, the basis of the exam question could be to do with describe the different shapes of transition metal complexes. Talk about the coordination number. Coordination number in these examples is the same, but the shape is different. Now, this last square planar one that we just looked at, this platinum ammonia chloride complex, is interesting because it can show cis-trans isomerism. So stereoisomerism is also important in transition metal chemistry. We've just shown you one example here. What I'd like to do is think, is this cis or trans? Trans, because when I look, if I look at the chlorines, they are 180 degrees away from each other. They're across the complex. Or I could be looking clearly, let's say the 2 ammonias, they are across the complex. Trans meaning across. I could, however, have arranged these so that the 2 identical things were 90 degrees away from each other. Cis. This complex has a special name. It's actually called plating, and this is is an example of cisplatin, transplatin. Cisplatin, really important compound, really powerful drug used in the treatment of cancer. And that's something you need to know. You need to know this as an example, not just of stereoisomerism for cis-trans isomerism of square planar molecules, square planar complexes, but you also need to know that cisplatin is used in treatment of cancer. So, cis-trans isomerism, a form of stereoisomerism using square planar complexes. Now, we also have cis-trans isomerism in octahedral complexes. As it says, with monodentate ligands. Now, what on earth are we talking about in terms of monodentate? Monodentate is a ligand that can form one dative covalent bond to a central metal ion. So monodentate is a ligand that is able to donate one pair of electrons to that central metal ion in the transition metal complex. So when I look at my octahedral complex here, I need to arrange my ligands in different ways. So what I'm going to do is put all of my ammonias like this, and then the fluoride ions 180 degrees away from each other. Because the fluoride ions do two different things, 6 ligands, 4 of one thing, 2 of something else. 2 of something else, in this case fluoride ions, are 180 degrees away from each other, so this is described as being trans. If I arrange the 2 different things at 90 degrees away from each other, I'll just put in all the ammonias. Because the chlorides in this example are 90 degrees away from each other, this is described as being cis. So I've cis cis-trans isomerism in square planar, cis-trans isomerism in octahedral. So a question that's about stereoisomerism, which is kind of becoming somewhat overdue in terms of OCR questions. A question to do with cis-trans isomerism could be asking you to explain it in terms of different shaped transition metal complexes, or with different, describe cis-trans isomerism in transition metal complexes with different coordination numbers. These have got, obviously, these octahedral ones have a coordination number of 6, the square planar have a coordination number 4. Good examples to learn. These are all mentioned on the syllabus. Oh, it gets worse, it gets worse. There's more, there's more. Cis-trans isomerism in octahedral complexes with bidentate ligand. Well, guess what? A bidentate ligand is a ligand that can form 2 dative covalent bonds to a central metal ion. So we've got a molecule or an ion that's behaving as a ligand that is able to form 2 dative covalent bonds to that central metal ion. In the syllabus since 2015, there is a specific example of a bidentate ligand that we are supposed to teach you. 1,2-diaminophane. So I'm going to do it skeletally because it's faster. So I've got 1,2-diaminoethane. The key point here is that the nitrogens, as well you know, in amines have a lone pair of electrons, which they are able to emit. In the old syllabus, we used to have to teach about another ligand that was bidentate, the ethane dioate ion. So again, we're going to have 2 carbons, and each of those carbons effectively is a carboxylic acid minus the proton. So I have this, think about this carboxylic acid. Carboxylic acid has lost a proton from each of the carboxylic acid groups, wherever you want to put that minus. But if we draw it skeletally, it's a little bit more straightforward. Each of the oxygens from the O- has a lone pair of electrons that it can use to make a dative covalent bond to the central metal ion. Now, the ethane dioate ion is not on the modern syllabus, but has been asked. For example, we've got the ethane 1,2-diamine. I'll find somewhere soon the example using the ethane dioate ion. Something that you've got to watch out for here, for example, is when they give you a molecule or ion that is kind of a hybrid of the two that we've just looked at. So when I look at this ligand here, I can see I've got an NH2 bonded to CH2, which is bonded to a carbon, double bonded to oxygen, and another oxygen with a minus sign on it. So the interesting thing about this bidentate ligand is it's kind of an amalgamation of the 2 ligands that I've just shown you. We've got the nitrogen with a lone pair of electrons, and then we've got the lone pair of electrons on the oxygen. So this is an absolute application type question. They're giving you a ligand that you've never come across before and are unlikely to have been taught in class. Now, in previous years, we have also had this as an example of a ligand. The key point is the same. We're looking out for oxygens, minus charge, lone pair of electrons. Nitrogen, lone pairs of electrons. These things can form dative covalent bonds to a central metal ion. So let's go back to our 1,2-diaminoethane. We're looking for cis-trans isomerism. So let's take some care now in trying to draw what's going on in these particular transition metal complexes. What would I do? Well, first of all, I put the bonds in so that I've got my octahedral structure. I've got two chlorines. They're monodentates. They form one dentate covalent bond each. These things, these bigger molecules, are the bidentate ligands. So I would stick the chlorines on first. This is in the trans position. Now they're in the cis position. What I've now got to do is attach my nitrogens, NH2, make sure that the nitrogen is at the end of the bond, NH2, and then draw in the rest of that particular molecule for that ligand. So NH2, NH2, slap it all in square brackets, and there's a residual charge plus 1. So NH2, NH2, same again. It may not look beautiful, but the examiner can see that it works. So my monodentate ligand was either on the left hand side 108 degrees away from each other or 90 degrees. Cis, trans. Cis transisomerism. In octahedral complexes where we have two bidentate and two monodentate ligands. A bit more complicated. But there's a question which comes up. For example, here. We've got a complex of iron, Fe3+, with two ethane 1,2 diamine ligands. Different name for the same, different way of naming the amine, and two chloride ligands. They've drawn the ethane 1,2 diamine or 1,2 diaminoethane, different ways of naming the same thing. That is cis transisomerism in octahedral structures. This looks exciting and interesting. Complex ion A has cis-trans stereoisomers. That's what we've just been discussing. One of these stereoisomers exists as an optical isomer. Optical isomerism in octahedral complexes with bidentate ligands. So this is the same molecule that this is the same transition metal complex that we've just drawn. And what we need to understand is if I go back to my cis form, it has to be the cis form. Get that cis form drawn. If I reflect this, perfectly, so I'm going to draw both of them at the same time. Those two structures are both cis, but they are mirror images of each other that are non-superimposable. So just like in organic chemistry, I can create optical isomers, mirror images that are non-superimposable, or if you like enantiomers, they are optical isomers, non-superimposable mirror images. Two bidentate ligands, two monodentate ligands. So this is kind of almost like the pinnacle of isomerism in transition metal complex chemistry. If I give you an octahedral complex with two bidentate ligands, two monodentate ligands, we can talk about cis transisomerism, and we can also talk about optical isomerism. The cis isomer has a mirror image that is non-superimposable. That is not true for the trans isomer. And our final example, if I take a transition metal complex, octahedral, that has three bidentate ligands, I can get optical isomerism. No cis-trans, just optical. And in this particular case, again, what I would suggest you do is draw both isomers simultaneously, reflect the bonds, and then you can put the groups on carefully so that you can reflect the groups. Let's draw that a little bit better. Square brackets. Now looking at that, I can see, looking at the picture for that, the ruthenium ion at the centre, 2+, the bidentate ligands have no charge in this case. Those two are perfect mirror images. They are non-superimposable mirror images, so they are optical isomers. So we have, this is where it's complicated, stereoisomerism in transition metal complexes. We can have cis-transisomerism in square plane, cis-transisomerism in octahedral. And that could be where all of the ligands are monodentate, or where two of the ligands are bidentate and two of the ligands are monodentate. In this case, where I've got an octahedral transition metal ion complex with two bidentate ligands and two monodentate ligands, besides cis-transisomerism, we can also have optical isomerism. If we just have three bidentate ligands, there's just optical isomerism. You need to be familiar with all of these because this is the kind of thing which can come up in questions to do with stereoisomerism. If, like the June 2022 paper that I've just shown you, they could give you structure. They could ask you to draw the structures and have given you or reminded of you of the types of ligand which are present. Worst case scenario, they could give you a 6-mark type question, a feature of which might be describe stereoisomerism in transition metal complexes. You've got to know the examples, you've got to be able to show cis-trans and optical isoms. Okay, we'll leave that video there.